Continuing metric spaces, lecture 2. In this lecture, we'll be discussing sphere or ball in open and close concept. So sphere or ball, first of all the definition, let XD be a metric space. Metric space is not just the set, it's an ordered pair with the metric, the non-empty set with the metric defined on it. And let A belongs to X be any fixed point. If R is any positive real number, then the set defined as the collection of elements of the metric space X belongs to X such that the metric of X from A is strictly less than R. Means there is an element A and there is a boundary in terms of radius R, and the elements lying inside this boundary, means the boundary points are not included, only interior points are included, then this set is called open sphere or open ball. See, by looking at this representation, it is very much clear, and sphere or ball is not always a sphere or ball geometrically. They can be in any shape. It's actually about the region. So we are talking about less than R metric, means the points lying in this interior portion, interior of the interval. Open ball can take any shape. It can be a shape of circle, a shape of line, a shape of kite. It can be anything. It's just a region. Region with the two specific things. One is center is fixed. Once taken, it's fixed, and it is also from the metric. And R is any positive real number which will provide us the boundary. So A is called center of sphere and R is called radius of sphere, and it is denoted by a few symbols S A comma R, center first and then radius, or we can say S A R and the R is at the bottom. Same kind we can write for B A R, because sphere and ball are the same thing in metric. So two specific things are center and radius. Now similarly, closed sphere or closed ball we can also define with a similar concept. The only change from open to close is that in open only interior points are included, and in closed interior plus boundary points both are included. So it contains elements of metric space X belongs to X such that the metric of X from A is less than equal to R. Equality gives the boundary points also. So the symbols are also the same with the close brackets. Or we can say, if you are writing BAR open, then make a closure above it. So this is a note. A ball is always non-empty, whether it is open or closed. Why? Because it always contains at least the center. If no points comes in the interior, at least center is in the ball. So sphere, whether it is open or closed, it's always non-empty. So the question is describe an open or and closed sphere for the usual matrices for R and R square, real and two-dimensional real. Usual matrices. First of all, this should be clear to you. What are usual matrices in different sets? In R, the usual metric is the simple distance formula, the positive side of it, dxy is equals to modulus of x minus y defined for any two elements of R. And in R2, suppose you take two elements in R2, both of them will be two-dimensional, x1, y1, x2, y2. And the metric is defined as z1 to z2, difference of the first coordinate square plus difference of the second coordinate whole square and complete under root. So under these matrices we'll be discussing the open and closed surfaces, open and closed spheres. So in first case, let x is equals to R, the usual metric, I'm writing it again because it was not visible with that pen, I noticed it later, defined by dxy is equals to modulus of x minus y for all x and y belongs to R. Let A belongs to R be any fixed number, then the open sphere with center A and radius R, as the definition suggests. I'm writing the definition. It contains those elements of the metric. The metric here is R, such that the distance metric from x to a is less than R. Now, applying the definition of the given metric here, modulus of x minus a less than R, opening the definition of modulus minus R to R, adding a in the inequality a minus R less than x less than a plus R, means the elements which lie from a minus R to a plus R are the part of this open sphere. A minus R to a plus R, this is an open interval. So for the metric R, open spheres are actually the open intervals, and they can be written as open interval a minus R, a plus R. A is the center, R is the radius. So for example, you need to find a sphere with 2 as a center, half as the radius. So by this solution above, for open sphere in R, we write the same criteria, mod x minus 2 less than half, or you can write simply directly the answer as open interval 2 minus half, 2 plus half, means it contains point from 3 by 2 to 5 by 2, right? So we need to find the region which is in open sphere. This is as per the definition, or you can write it directly, a minus R, a plus R, open interval. So this was the open sphere case I discussed before. Now the closed sphere in a similar manner. If you are talking about the usual metric of R, the closed sphere is given by the closed interval a minus R, a plus R, because in the same definition of metric it will contain less than equal to R points. Less than equal to R points will give you closed interval a minus R to a plus R. Now for the second part, when you are discussing the usual metric for R2, two-dimensional space, the usual metric for R2 is defined as, suppose there are 2 points z1 and z2 belongings to R2, and z1 is x1 y1 and z2 is x2 y2. So this is the metric given in R2. Now solving this for center and radius. So center will also be belonging to the metric space. Let A be the center of R2. Then A is also two-dimensional. We'll be writing A as x0, y0, suppose. And now the open sphere, if I want to discuss with center A and radius R. R is a real number naturally. So this is given by those elements of R2 space. So now elements also be two-dimensional, x comma y, let this be z. It contains z kind of elements in R2 such that the metric from z to a is less than R. Now substituting the definition, z is xy, a is x0, y0, as per the definition of the metric given above, it will be x minus x0 whole square plus y minus y0 whole square root and less than R. Squaring both sides will be getting equation of a circle with center x0, y0 and radius R. Circle or a disc, you may say. So suppose this is the representation of R2 space. Center A is at the point x0, y0, and we are discussing the points lying in the interior of this circle whose center is x0, y0 and radius is R. This will provide us the open sphere in this case. So the open sphere in this case contains all the points which lie inside the circle x minus x0 whole square plus y minus y0 whole square is equals to R square. Only interior points are included for open sphere. And when you are talking about the closed sphere, the interior plus boundary points both are included for closed sphere. Similarly, closed sphere with center A and radius R, in this case, is the set of all points of R2 space which lie within and on the circumference of this circle or disc The equation of the circle is x minus x naught square plus y minus y naught square is equals to r square. So in this case it is a shape of a circle, right? We'll discuss further example which may take different shapes also for open sphere and closed